Hi, today I'm going to talk about data plane benchmarking in NFV environments. As we transition from traditional network devices to NFV world where network functions are implemented as VNFs, one of the key challenges that VNF vendors and service providers are facing is to ensure that NFV can provide the performance and reliability offered by traditional network devices. Let us look at some of the key aspects of data plane benchmarking in NFV. So one of the key factors that impact performance in NFV is the assignment of compute node resources to virtual switches and VNFs. Considering that infrastructure is shared, in order to get consistent and improved performance for virtual switch and VNFs, we need to ensure performance isolation. Essentially, there should be minimum performance impact of a given VNF on other VNFs residing on the same compute node. So to ensure such behavior, CPU core pinning or assigning dedicated CPU cores to virtual switch and VNFs is important. Now, NUMA refers to an architecture where a set of processors or cores have been assigned their own memory and I/O channels. Although processors or CPU cores can access memory from another NUMA node, it has a cost associated with it. It introduces additional latency, which can impact the forwarding performance of the associated network function. So because of this reason, it is recommended to assign virtual switch and associated VNFs to the same NUMA node. And similarly, the associated network interfaces should be assigned to the same node for performance optimization. In addition to the CPU core assignment and the CPU processing power, is that the only factor which impacts the forwarding performance in NFV environments? Effective utilization of the queues at the network interfaces and hashing algorithms employed can also impact the performance, along with the ability to avoid issues such as out of sequence packets for the given traffic flow. So for instance, understanding what impact the frame size has on forwarding performance. For smaller frame sizes, performance is CPU bound, whereas for larger frame sizes, performance is limited by network interface bandwidth, or how effectively the queues are utilized, or what type of hashing algorithm is employed. Now, if the hashing algorithm utilizes only IP addresses and port numbers, then if the flows are based on MAC addresses, is there effective utilization of the queues? And is the network interface bandwidth a limiting factor for the forwarding performance of the vSwitches or the NFV environment? So there are multiple test scenarios where the traffic could originate from a virtual network interface and terminate on a physical interface. It could originate from a physical interface and terminate on a virtual interface. It could be originating as well as terminating on a physical, or it could be originating on terminating from virtual, right? In all these scenarios, we want to make sure that we benchmark all different deployment scenarios. To do that, we need to have a test endpoint which can be connected to the physical interface of the compute node. At the same time, we need to have a virtual test endpoint as well. Here's a list of test cases identified by VSPerf working group at OPNFV. A good number of these test cases are based on the benchmarking standards such as RFC 2544 and RFC 2889. But there are additional test cases such as throughput profile, flow scalability, memory impact on forwarding performance, CPU usage impact on forwarding performance, and control plane data plane coupling. I'm listing some of the key methodologies here, which I will be talking about in detail in later sessions. So when we look at performance consistency, it's expected to be there in traditional network devices. But for virtual network functions or virtual switches, this is not necessarily the case. NFV has a shared infrastructure, which makes consistent performance a challenge. Now, optimization can be achieved by isolating the compute and network resource allocation to VNFs, which we talked about earlier briefly. But still, performance consistency is a paramount benchmark and a key factor for resource provisioning and capacity planning. And Similarly, initial packet latency measures the latency of the first packet as it may vary across vSwitch implementations. Flow scale measures the forwarding performance at various flow scale levels. Throughput and latency profile test evaluates the forwarding performance if it degrades as the offered load varies in the region of the maximum forwarding rate. In packet delay characterization, min, max, and average is not enough to determine the anomalies for various frame sizes and flow sizes. Information such as how many percentage of packets had delay more than a specified threshold is an important measure. With this, I want to end the high-level overview of data plane benchmarking for NFV. In subsequent sessions, I will cover some of these methodologies in detail and how to set up these methodologies and run these methodologies in Spirent Methodology Center.